Now that we have finished learning about the mechanisms of dissociation and ionization reactions, it's time to look at how to do stoichiometry calculations involving solutions. The problem is, if we wanted to use the molar mass of the solute, copper 2 sulfate in this case, in the calculations, we can't do this directly because the mass of each of these solutions is not just the mass of the solute, it also includes the water in which the solute is dissolved. However, we can still tell that these two solutions do not have the same amount of solute in them. If you had to guess which of these two solutions has more CuSO4 dissolved in it, if you said that the Erlenmeyer flask on the right has more solute dissolved in it, your instincts have served you well. Most of you probably figured this out because the solution is darker, indicating that there is more CuSO4 dissolved in this volume than there is in the volume on the left. This visual difference illustrates a difference in what we call molar concentration, known more succinctly as molarity. The units for molarity, or the formula to calculate it, simply involve taking the moles of solute that exist and dividing it by the volume of solvent in which we dissolve the solute. Remembering that, of course, the solvent 99% of the time in solution chemistry is going to be water. The units for which come out as being moles of solute divided by the volume of water in liters that make up the solvent. Instead of writing moles per liter, molarity can also be written as the unit capital M. Alternatively, there may not be any units given at all, and there may be square brackets used like this surrounding either the solute itself or the separate ions that it dissociates into. If you see any of these three measurements, moles divided by liters, capital M, or the solute surrounded by square brackets, all of these are asking for you to calculate concentration. Doing a stoichiometry calculation involving a solution is actually relatively straightforward because they only involve one additional step of dividing by the volume of our solvent. Now, in this case, we should always start by finding a balanced equation, and since we know how dissociation reactions work, we will take CuSO4 and break it into the two separate ions into which it separates, copper with a positive charge of 2, and sulfate with a negative charge of 2. And we can see the most important part about finding the balanced reaction is that the mole ratio of each of our compounds and ions is 1 to 1 to 1. And from here, we now have a foundation to solve for the concentration of each of the ions in solution. The problem is that our initial measurement of copper 2 sulfate is given in grams, where our concentration formula requires us to use moles. So we need to figure out what the molar mass is and multiply by 1 mole over that molar mass. So let's go to our periodic table. We see that the molar mass of copper is 63.55, molar mass of sulfur is 32.07, and the molar mass of oxygen is 16. So we can solve a little arithmetic in order to figure out what our molar mass is. Remember that we have 4 oxygens, so 16 times 4 is 64. And if we work through a little bit of arithmetic here, you will find that the molar mass of copper 2 sulfate comes to 159.62 grams. If we divide by the molar mass here, that gives us the amount of moles of CuSO4. And then what we're going to do here, since the question asked for the moles per liter of copper ions and sulfate ions, we can quickly add another conversion factor here. Let's start with copper ions just because it's first in the equation. And for every 1 copper 2 sulfate that is dissolved in solution, we get 1 copper ion like this, because again, there's only one copper ion in the compound here. So again, this conversion factor doesn't actually change any of the numbers. It just changes our reference point about which ion or which compound we're looking at. Now that we've calculated the moles of copper 2 plus that we have, all that remains is to divide by the volume of our solution, which is 575 milliliters of water. Those with a keen eye will recognize that our units for volume are wrong, because the standard units for molarity are moles divided by liters, which means we need to convert this volume here into liters, which we can do by multiplying by 1 liter over 1,000 milliliters, which is the same as taking 575 milliliters and dividing by 1,000 to get liters, which comes to exactly 0.575 liters. This is the only time I'm going to show this. From this point on, I'm going to assume that you can calculate milliliters to liters conversions in your head, and I will henceforth be just writing the volume out in liters, assuming that everybody knows how to do that. When you put all of this into your calculator, before we do that, let's check our units. We have moles of copper 2 plus ions in the numerator divided by the volume of water in our denominator. That matches our units, moles per liter. And if you put this into your calculator and round to 3 significant digits like we see in our measurements, this comes to approximately 0.0830 moles of Cu2 plus per liter. So in a concluding statement, we can simply write that the concentration of Cu2 plus in moles per liter is approximately equal to 0.08300 moles per liter. Now, we're actually done the question because we know that our moles of Cu2 plus and our moles of SO4 2 minus are going to be equal, which means we can simply say that this number is equal to the concentration of Cu2 plus, which is also equal to the moles per liter of SO4 2 minus, and we have successfully identified the concentration of both. In the next video, we're going to look at what happens when we not only dissolve a specific solute within a specific volume of solvent, but when we want to add water in order to change what this concentration is, which is what is known as a dilution.